All right, so I mentioned that there's not, there is sort of a strict geometric definition of an ellipse where we're defining it as the set of all points that have some relationship to two focal points, two foci. And so far, I haven't mentioned that at all. Like, we haven't talked about that. I just mentioned it once in the beginning. But the last few videos, we've just been talking about the stretching and the shifting and talking about, like, how that works with with the ellipses, right? The dimensions and the equation. But a lot of the applications that you use involving ellipses require that we know where the foci are. And so we need to start looking at that geometric definition and kind of approach ellipses in a slightly different way so that we can understand where the foci are and how the shape is related to them. So I'm going to plot some foci in there. For this ellipse right here, first of all, the foci are always going to be inside the ellipse, and they're always going to be on the major axis. This ellipse I've drawn is centered at the origin. We're just going to keep it centered at the origin for now to keep things simple, but all these points could be shifted elsewhere if you move the center. Okay. But the foci will always be on the major axis inside, and they're always the same distance away from the vertices on the left and the right. So this distance here and the distance on the other side are going to be the same. So our foci are sort of somewhere like that. I'm going to call them F1 and F2. That's a common labeling for foci. So now, the geometric definition of the ellipse says that if you take a point somewhere on the ellipse, let's grab a point, like say here, for example. If you take that point xy, and you measure the distance back to each focus, so there's one, and then there's the other. Those two distances, let's call them distance 1 and distance 2. Distance 1 plus distance 2 are going to add up to a constant. Okay, and the value of that constant affects how big the ellipse is, as well as, of course, the location of the foci. So you can keep these foci in exactly the same place, and if you make that constant bigger, the ellipse is going to get kind of bigger, right? Because the string will be longer, right? The string, the imaginary string that connects these things together. All right, that's fine, but the question is, what is that constant? For this particular ellipse, what is that constant? If the constant somehow affects the size of the ellipse, then we should be able to figure out what the constant is in terms of the like dimensions of the ellipse, like the a value and the b value that we have here, right? So let's look at another location you could move that string to. Let's grab this point over here. Okay, imagine you can move your pencil around this ellipse and trace out the ellipse with the string always connecting the pencil back to the two foci. So one half of the string is going to be here connected to this focus, and the other half of the string is going to come all the way down and connect to that focus. So the string is going to be stuck out like that, and it can loop over your pencil and come back. So those two distances should add up to our constant, except in this case, now that we're putting them all horizontal, we can actually say, we can actually measure what those distances are in terms of our positions and things here. But to do that, we need a little more information in here. We need to get in here and say what the coordinates of the foci are. So focus 1 and focus 2. I remember I mentioned that this distance is the same on both sides. So also the distance from the center, which is currently the origin, is the same on both sides. So that is called A and that is called B. And then the distance from the center to the focus is going to be called C. So this is going to be at negative C0 and this is going to be at positive C0, like that. So that's C, all right? And so now what we're going to do is with the A, the B, and the C, we're going to try to figure out what that constant equals. So first of all, this little short distance here is basically the A distance minus the C, right? If you take A and then subtract C, then you get what's left over. So that is going to be A minus C. I'll label that. The other one is that total distance there. That's A, right, from the center to this end this endpoint on the ellipse, and then plus that distance. That distance was c. So that's a plus c. Okay. So the two distances added together, in this case, are a plus c plus a minus c. The c's cancel, and we just have a plus a, which is 2a. 2a, which is actually the length of the major axis, right? A is half the major axis. So the whole major axis is of length 2a. So it turns out that the length of that string, that constant we were looking for, that constant string length equals 2a, the length of the major axis from one end to the other end. So there we go. So now we've got that. Now we can start putting things together. We're going to do one more possible string position here. And that is, we're gonna put our pencil right up at the top right here. And we're gonna go like this and pretend that our string is connecting from that point all the way down to the foci on each side. And now, armed with this knowledge that the constant length of that string is 2a, if we put our pencil right at the top right here at this point in the end of the minor axis, then the distance back to each foci is actually the same on both sides, right? They're equal because we have this symmetry. So that's exactly half of 2a, which would be a itself. And this would be a on this side. So what we actually have now, and I'm going to draw another version of this picture, is we actually have this distance here is b, this distance here is c, and then if you connect these with a line, a straight line, that distance there, it turns out, is a, which is also, by the way, that distance, a. So a is both this distance here, and also if you kind of shift it around, it's going to be that distance right there. Those will be the same. But looking inside here, we now have a little right triangle, like that. And looking at that right triangle, the sides, the legs of it are b and c, and the hypotenuse is a. So we can actually pull in Pythagoras and do the Pythagorean theorem on those numbers and get b squared plus c squared equals a squared. Or more commonly, c squared is a squared minus b squared. And that gives us a nice algebraic relationship between the dimensions of the ellipse, the a, like the a dimension and the b dimension, and then the distance from the center to a focus. So this is super key. This thing right here, kabam, 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 this relationship specifically for ellipses is what tells us basically where the foci are, right? If you know the dimensions of the ellipse, this can tell you, you can plug in the a and the b values, calculate the c value, and figure out where your foci are. As long as you also remember that they're always on the major axis, an equal distance away from the center on each side, and that c is that distance. So this kind of gives us a bunch of information about ellipses. We've now got this notion of like the three different measurements that matter for an ellipse. There's the a, the b, and the c. Turns out if you going back to the purple here, if you go ahead and calculate the d1 plus d2 and set that equal to 2a, what you get is a square root of, let's see, x minus negative c squared plus y squared, and then plus another square root for distance 2, where it'll be x minus positive c squared plus y squared. Set that equal to 2a. And then combined with this relationship here, you can do a bunch of algebra, which I'm not going to go through in this video, and actually, starting from that information alone, arrive at the same equation. It's the same equation, x squared over a squared plus y squared over b squared equals 1. So that's how an equation can be derived from the geometric definition, okay, using all this jazz. So if you want to see the details of this proof in between here, you can go check out the textbook. The section 12.1 ellipses goes over all this, and you can look at all those details. It is a long algebra mess, but it is kind of illuminating. I've just given you what I think are the sort of key ideas behind it, which I would like you to know about.